Welcome back, calculus student. Hoping everything's been going well for you as far as your homework is concerned. Give me just 1 second to rearrange my camera so that everything can be seen as well as possible. Okay, so we're looking at this as our problem, and but we're going to talk about the second derivative now. What the second derivative is it's the rate of change of the rate of change. Again, the first derivative is the rate of change of something. Well, the rate of change of the rate of change is what the second derivative shows. We talked about that with acceleration. Acceleration is how or measures the rate at which velocity changes. Velocity being the first derivative of position, so acceleration is the derivative of velocity. Well, you have this concept called concavity, and when asked about concavity, a lot of people think that that is a prisoner's tooth problem, but concavity means more than just that. What concavity does is you've got a problem right here. Now this problem right here is increasing. And it's increasing really steeply at first, but as it goes, it's still increasing, but it's not increasing quite as rapidly. Now, this is what's referred to as being concave down. This would have a second derivative that is negative. All right, something that is concave up might look like this. Here we have something, again, it's increasing. Not all concavity deals with increasing, but this is increasing, and as it's increasing, it increases slowly here, but notice how it's getting steeper and steeper and steeper as we go here. So this has a positive concavity. Its second derivative is going to be positive because it's increasing at a faster rate. Now, likewise, you can have concavity with decreasing values. I'll give you just a second to think about this without me doing any problems, but think about this. Would this have a second derivative that's positive, or would it have a second derivative that is negative? Well, as we look at it, this one has a second derivative that is actually going to be negative. I'm sorry. Yeah. Okay. So this is concave down. It's decreasing at a slow rate, but if you think about what decreasing means, decreasing is negative. So it's decreasing at a slow rate, and now it decreases at a faster rate. So it's got a concavity, because this is talking about decreasing, that is going to have a second derivative that is negative. So it's concave down, concave up, and decreasing would look something like this. Yeah, it's decreasing. These are very steep negative values, and then you have less steep negative values. So it's decreasing at a faster rate. So it's decreasing. Yes, it's decreasing at a fast rate because it's getting more and more closer and closer to zero, closer and closer to a positive number. So its concavity is positive. So this is decreasing in concave up. This is decreasing in concave down. Now, let's look at this problem. Pause your video for just a second, and just after I'm quiet, take this, set this, solve for the second derivative of this function while you pause the video. Okay, now that you have finished pausing the video, this is where I have solved out the problem. I've got the first derivative, again, quotient rule. I get the first derivative to be negative 12x times x squared plus 3 quantity squared. Second derivative is a little more involved. Again, we don't want to square this out, because if we square out the denominator, we lose the fact that we're going to have at this step an x squared plus 3 cancel out with a factor of x squared plus 3 here. So all that goes away, and in the end, we get that the second derivative is 36 times the quantity of x plus 1 times the quantity of x minus 1 over x squared plus 3. Now, if you didn't get that, please pause the video again, try to rework through the problem. Now, let's look at determining from this the concavity. Just like with the critical number, we want to see concavity can change either where the second derivative is 0 or the second derivative is undefined, because again, we're talking about switching from positive values to negative values. So let's talk about where this second derivative would be undefined. Well, it would be undefined where the denominator is 0. This denominator, if you set x squared plus, sorry, I'm allergic to math. If you set this x squared plus 3 equal to 0, you'd have x squared equals to negative 3, so x equals the square root of negative 3, which would not, plus or minus, but doesn't matter. This is not going to be undefined anywhere. But the second derivative will equal to 0 at negative 1 and positive 1. So let's look at putting those values on the number line. So I've got 36 times x squared minus 1, I'm going to rewrite it as that, over x squared plus 3. And on my number line, I'm going to put negative 1 and I'm going to put positive 1. Now, let's take test numbers in each one of these intervals. So I'm going to test a number like negative 2, because negative 2 would be in the interval from negative infinity to negative 1. So if I plug in negative 2 squared is 4, 4 minus 1 is positive 3. I've got a positive times a positive, which is positive. And in the denominator, I'm always going to have a positive value, because the smallest this could ever be is 0. And 0 plus 3 is always going to be positive. So I've got a positive over a positive, so it's positive. So this would be concave up. All right, now I go to 0. If I take 0, I've got 36. 0 minus 1 is negative, so I have a positive times a negative, which is negative. And then, of course, the denominator is positive, so this is a negative quantity here, so we would say that this is concave down. And finally, if I plug in 2, that's positive, 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 so concave up. Now, the points where our concavity changes at negative 1 and our concavity changes at positive 1. So I could say we are concave up from negative infinity to negative 1, and then 1 to infinity. And I'm concave down from negative 1 to positive 1. All right. Now, the points where this happens are called the points of inflection. Points of inflection. Because a change of concavity looks something like this. Here we're concave up, and then here we're concave down. So right about here is where the second derivative is either equal to 0 or it's undefined. So, sorry, about to sneeze again. Anyway, this is going to be my point of inflection. Now, to know what that point of inflection is, we plug in to the original problem. So, we've got 6 times negative 1 squared plus 3, which would be 6 over, that would be 1 plus 3 is 4. So I'd have 3 halves. And then 6 over 1 squared plus 3. Again, plugging back into the original, I get 6/4 again, which would be 3 halves. So my 2 points of inflection are at negative 1 3 halves and 1 3 halves. Now, a point of inflection is a point that actually has to be on the line itself. It has to be defined in the domain. So that's the first example. I'll do another example in just a second on another video.